All right, welcome to another video. Hopefully the microphone is good enough. I just took a shower and I kind of don't want the headphones on my wet hair. It feels kind of uncomfortable. So let's continue on with this exercise about configuring large BGP communities. So where we left off, I think I just got the basic right. So what we were trying to do is make sure that we've got management set up to all of these networks so that we can configure them without having to counsel and do out-of-band management. We want to do in-band management because we want it to be as similar to the real world as we can get. So it looks like, unfortunately, it's erased all my configurations, but I've got them in my scroll back buffer here, so I can just add them again. So one of my favorite Linux commands is history, so I can do history pipe.config, and it'll pop up. Looks like it was, let's see here. So this command here, 24, looks like the one that was successful, so I can just do !24, and it will run that command again for me. And then this one is just 2 steps up in my buffer, so hopefully now I am good to go. So let's try to ping those addresses in the autonomous system. Okay, and now let's try. So that was that one. So yeah, that's all we need to do. Last time we saw kind of a fun exercise. We noticed that it was missing right. On router 2, the one that the management server was hooked up to, OSPF was not advertising that extra interface here that goes to the management server. So we weren't able to get to router 1. Well, we were able to get to router 1. That was kind of the point of the video, is that we were able to get all the way to router 1. But when we got there, since we weren't advertising that network that connects to the management server, router 1 didn't have an entry for it in its routing table. It had a no route to host message when it tried to respond, but it had no way to send that back to the management server, so we just got a timeout. All right, but everything's good now. You can see the management network is learned via OSPF. Let's do one more step in this management setup. And let's make it so that we're going to connect to these devices on their loopback addresses instead of their interface addresses. This is generally considered a best practice. It's generally not considered the best way to serve management to a device through their physical address, because the loopback address is going to change less if we place a link, or we add a new link, or we want to convert it to a port channel or something. That loopback address isn't going to go through any changes. Also, if we want to set up different kinds of IGP routing, again, that loopback address will not go through as many changes in that case. So let's advertise the loopback address in the OSPF. And oh, well, we've got to put the IP address on it first. Okay, so we've got the IP address now. is on the loopback interface. So now let's advertise that into OSPF. And we don't need any OSPF traffic to go from LO00. We just need the network on LO0.0 to be advertised out to other routers. So let's include the passive command, which is do not run OSPF, but advertise it. All right, so now that's all we're going to need for the loopback to be reachable from the management server. So let's try to ping that. Perfect. But of course, we're not going to be able to ping the 1.2.2 yet because we haven't learned that route through OSPF. All right, so now we're going to be set up on router 2. Perfect. So now let's create some manual static mappings in DNS on this management server so that it's nice and easy to SSH into those devices. So that's going to be in the etc hosts file. Okay, so now we can ping router 1 and we can ping router 2. So let's set up SSH on these routers next for remote management. And let's have the user be named management. And then for the authentication method, we're going to be using SSH RSA. And of course, we're going to need the string of the public key, but we don't have that yet because we haven't generated our keys. So let's generate those keys. So SSH, and then it's going to be key gen. So now we need to specify what kind of keys we want to generate. We want to generate RSA keys. And you can see we've got a lot of different kinds: DSA, ECDSA, ED25519, but we're going to go with RSA. And those are all available options on the Linux server as well. I just don't see them. Yes, I see them now. DSA, ECDSA, ED25519, RSA, and we also have an extra option on the Linux server for RSA1, but we're only going to need RSA. So bits, we got to specify the bits, and as we saw in our marathon session to try to get this to work the first time, it's got to be 2048 because that's the default number of bits that's used on Juniper. I'm sure there's a way to change it, but 254 is generally considered secure enough. I think, actually, I'm not sure about that. I know a lot of guys say to use 4096, but we'll just go 2048. In a production environment, you probably are better off with, I mean, the higher you have, of course, the more secure it's going to be. But again, it's a trade-off because you're exchanging more information. So security is always a trade-off between convenience. It's always, you kind of pay for your security in convenience. So it just depends how much of an investment you think is necessary to make in security. And a lot of production environments have additional layers of security. So it's not like this is your only means of securing that SSH session. It's just the extra step. Often people wouldn't be able to get on the management network because that would be locked down behind a firewall and it wouldn't be publicly accessible. All right. But of course, if there's any IP on the routers that are publicly accessible, you can use that as a launching point onto their private network somehow. I mean, there's always, if there's a will, there's a way, of course. But the point of having security is to try to reduce those ways and hopefully eliminate them. All right, so now we need to specify what kind of keys we want. We want RSAs. Oops. So, oh, right, and it's going to be a -T. Perfect. So default, don't need a passphrase. So there's our keys. So now let's see what the key actually is. The public key, you don't need to look at the private key. That's got to be kept secret. So here's the public key. So we're going to need to, fortunately, we can't just do the whole thing in because it's usually not, doesn't kind of play nice that way. All right, so that's all we're going to need. We're going to need it to be in quotes, of course. All right, so it's just 6 lines of pasting in, not too bad. Oops, and we don't want the new line character in there. Perfect, so everything went through nice and easy. I believe that's all that's going to be needed. We might need to actually disable, oh, right, so that's nice that there's a good message there. We're going to need to include user management. And that word class is a little bit not kind of the best word to explain what's actually going to be happening, but this is just, well, okay, so here, yeah, permissions. So all that means is we're going to give this user a certain level of permissions. So we're going to give them super user permissions in this case, but if you were in a production environment, you would want to give the appropriate permissions to the appropriate groups of people. Your advanced engineers, people you're going to trust to make configurations or trust not to make configurations. You're going to give them their super user, but your NOC, your people taking in that first line of troubleshooting, they only need read only, and then if there's a fix, they can escalate that, especially if you have a maintenance window system and you only want changes to be happening during that. You give your night team super user, and then anyone who's on the devices during the day, you don't want that temptation of them going and making changes, so you just give them read-only permissions. In an ideal environment, you can just kind of trust people to not abuse their permissions. But if you, there's no reason to do that, like people having the appropriate level of position. I mean, it's all right there. It's on every equipment. It's really just kind of lazy administration if you don't do that, and it could lead to problems, because one kind of philosophy in IT that I learned in networking school, and that's kind of prevalent throughout it, is to reward people. So to reward people, you give them extra things. So if you give somebody super user full permissions, how are you going to, reward them by giving something extra? They already have everything. So you've got to give people the lowest amount of access and authorization they need to do their jobs. And then if it just so happens that they need something more, you can give them something extra, and that is a positive thing you are doing. Instead of having to take things away later and then having to justify why it needs to be taken away, they justify to you why it's necessary, and you grant it to them. That's a much better situation to be in as an administrator. All right. Now I might need to disable password off as well, because I think password off takes precedence over non-password off. And our form of non-password off, as we saw, is going to be by SSH RSA public key. All right, so it looks like we're missing a number of things. The other thing it looks like we're missing, if we go back to the management server, you can see it says connection refused. So I'll give you a second. 3, 2, 1. Okay, so the reason it says connection refused is because we never enabled the SSH service on this router. So another really good command that I hope is on this server, though the server has been kind of fun to use, so it's probably not on this server. Yeah, it is nmap, and with nmap, it'll show you which services are enabled on a remote device, and we would see that SSH on port 222 is not enabled until we go and do the set system services SSH command. Now we have enabled SSH after the commit, but we're going to need one more command, and that's going to be let's actually see if we need that command. So the last command we will likely need, and here's our keys, and it looks like we generated all kinds of keys. We only needed the RSA key, so unfortunately we're going to have some extra junk on the device that we don't need, but it looks like it doesn't make the running config any more difficult to see, so it's not something I'm going to worry about. So that's all we need. We don't need to disable the SSH password authentication. It will automatically do the keys. It's just in the last video where I was figuring out how to get this to work, I had a bunch of extra commands that were unnecessary just because I was kind of winging it by the seat of my pants, and I didn't really know which commands were necessary and which were not. But we can see nice and clean in this video, all we need is to set up the user, give it permission, so it'll automatically assign the user an ID. Then we need to set up authentication, which we're going to use public key authentication. We need to enable the SSH server, and that's it. So it's just 3 commands are necessary, and you've got very secure remote administration enabled. So let's do the same thing on router 2. We're going to do set system user, set system login user mgmt class super user. There we go. And then the user ID is going to be created automatically after we commit. So now we'll need to enable SSH, set system set system services SSH. Okay, and now we'll need to set up authentication for the user. Set system login user mgmt authentication RSA SSH-RSA. Okay, that's it. So let's add that key in there now. Perfect. Oops. There we go. Excellent. Okay. So just those 3 lines is all we need. Really nice and easy. So let's see if that worked. Oh, we've got to get the key, of course. You can get that public key automatically if you go in from the other side. So that might be kind of a way we could do it here to get the public key automatically, because there is SSH on the server. So 172.19.0.2. Oh, okay. So SSH is actually not enabled on this server. We can only form SSH connections from the server, but we can't form it to the server. So that's another good kind of security principle. It's like these don't really need to form SSH to the server, so there's kind of no reason to have it. Of course, you're not going, the same rules apply with this server. You're not going to console into the server. So you will need to enable SSH for people accessing the server from their workstations. Yes, if you have a keyboard and mouse hooked up to the server, you can do it that way, but often that is not the case. So yeah, we're good. Let's continue on with the exercise and configure the rest of the configuration. So now we can close the windows for the routers, and we can just use in-band configuration. And then if there's a mistake that cuts off our legs, we'll see that, and that'll be a really good learning experience. All right, so we've already got the configuration. Looks like we don't have the primary keyword set up. Let's put that on there. Now, one thing to kind of know is this is really risky config because we've already got this set up. It's working. Changing the IP is a bad idea on the IP that you're SSH'd to, but we're just making it a primary IP and it's already primary, so that's not going to be a huge deal. But one thing you'll see that I did do is it's a risky config. I did it in its own commit because I want to know if that's what causes me to lose my legs, if I lose my legs. And the other thing I could do, of course, is a configure exclusive. And then anything I'm not sure about, I can do commit confirmed and give it 1 minute. If I lose my legs, then in 1 minute it'll roll back. If I don't lose my legs, I can do a commit and it will go into the config. So that's always something I will advocate. As I've said in previous videos, though, configure exclusive can be something that's not ideal in a production environment, especially if you have automatic user accounts going in through some script or something and trying to gather stats every 15 minutes or something. You're going to lock those out. So often that's not really a practical command to use in a production environment. And here's that large keyword. So this just enables us to use more octets in our community string. A regular community just has 2 octets. Sorry, 4 octets. Each of these is 2 octets long. A extended community will have 8 octets. So this will be actually 4 octets long. And then a large community allows for 12 bytes. So the same size as a MAC address, it's going to be 6 octets. No, it's going to be 12 octets. Yeah, because a byte is an octet. So it's going to be 12 octets. Anytime I make a mistake, please call me out in the comments below. I will not be offended. I will be very happy because I just want to get the truth out, and often I might accidentally not do that. And if that is what I do, that is not something that I want to. Oops. Shoot. I think a better way to do this. Oh, okay. And it looks like I actually have finished the configuration for the .2 network. So a better way to do this is to actually go into the hierarchy. There we go. Okay, these all have the same next hop. That's kind of why I was confused there. And then these are not going to have large communities. They're just going to have the regular community strings. Oops. One thing I actually forgot to mention that I have learned only from experience, and is something that people might not ever encounter. Hopefully you would never encounter, but sometimes when you paste in large amounts of configuration at one time, the device can be processing those. And then if another user logs in, like a bot or something, and pulls information back, it can cause problems. This is on one particular kind of gear I was on, extreme gear. But in any case, I would say the best practice would be to only paste in a few lines at a time, really contentious configuration, just one line at a time, because pasting in multiple lines, first of all, you don't get a chance to to see, you don't get that last second chance to make sure that they're exactly what you wanted in there. Not only that, sometimes if the device is busy processing a large amount of commands that have all been put on there, it will not be able to properly respond to other things and might even trigger a bug. I will say one of the kind of worst things that can happen in production is a bug. They are rare, but they are devastating when they happen. All right. Okay, and a lot of these I already have because I set up management. So unfortunately, I just kind of typed them out. I need to kind of get out of that habit though, because I don't want to. I want to be able to think about what I'm actually doing when I'm on the test. I don't want to just have it, you know, a few things all ready to go. I sit down on the test. None of those things are on the test. I'm screwed. I want to be able to think and understand what I'm doing, and especially during the troubleshooting portion. But you can see this is the only actual changes I made. I added some more simulated traffic, and then I added a router ID and an autonomous system ID. I'm surprised I didn't set up an eBGP connection. I thought that was one of the, oh, okay, so this is router 2. Okay, so router 2 is going to be the one on top. I'm constantly thinking of it, router 1, router 2, router 3, but it's actually one in the middle, router 2, router 3. So it's kind of throwing me for a loop. All right, so router 3, as I mentioned before, it's in a different autonomous system. So responsibility for management is going to be handled by a separate party. So let's mimic that separate party by setting up a second management server. It might take too long. I mean, we already kind of drove home the point of using a management server. So if this is going to cost a lot of extra time, I'd rather just skip it. So let's skip it and just move on to router 3 and configure it using out of band management instead of in band management. Oops. So the concept of extended and large really seems kind of simple. It's just about how many octets or how many bytes, same thing, that you get to use as a community string. The reason you would need them, of course, is where it's kind of complex. Extended communities are going to be required in a VPN situation. I'm not too sure about large communities. I'm going to need to do some more research on that. All right, so everything looks good to go on here. So we've got the step-by-step procedure. Before we do that, let's see if there's any kind of clue about why you would need a BGP large community, especially when you have an extended community and that is all you need for VPNs. Like, what else would you need if you already got VPNs covered? Time to take action? What does that mean? Clickbait. I clicked on it. I'll just delete it. I'm sure I've got everything I need to. Here we go. So BGP large communities are a novel way to signal information between networks. Large BGP communities are, okay, well, tell me more about why. Here we go. Inspiration, so let's go straight to the RFC. As I've said many times before, RFCs are often your best bets. This actually looks like an interesting article, not quite clickbait. But let's go straight to the RFC. Maybe there's even a section on why you would need it. All right, maybe the introduction has it. BGP large communities provide a mechanism to signal opaque information between and within autonomous systems in very much the same way that RFC 1998, and I believe that's the one for extended communities, and then 1997 is just for regular communities, provides a concrete real-world application for BGP communities, RFC 1997. 1997 should be really familiar because we've looked this over in previous videos. 1998, that I don't think we've looked at. It looks like it's not for extended communities. This document presents examples of how operators might utilize BGP large communities to achieve various goals. So the opaque nature of BGP large communities allows for rapid deployment of new features or changes to the routing policy that perform an action. Operators are encouraged to publicly publish and maintain documentation on the purpose of each BGP large community, both informational and action, that they support or that are visible in BGP RIBs. Okay, so it's just more things you can do. It's just that turned out to be BGP communities a really useful feature, but it only had 2 bytes. So they wanted to push it out to 6 bytes so that it can be even more useful. let's read this one because it, you know, even this is a little bit clickbaity. It looks like it does have some kind of cool graphs and some good stuff in it. So probably won't read the whole thing, but hopefully we can take away from it a good sense of why large communities are really important. IPv4 addresses are not the only internet number resource that has effectively run out in recent times. Another pool of internet numbers under similar consumption pressures has been the numbers that are intended to uniquely identify each network in the internet's inter-domain routing space. These are autonomous system numbers. I actually often wondered about that because an autonomous system number, from what I understand, is like 1 octet. It's really small, and there's a lot of businesses that would have autonomous systems. So let's just keep reading. Like IPv4 address runout, the exhaustion of ASN number pool was a well-forecasted event, and in the same way that IPv6 was developed in response to the address runout, changes have been made to the BGP routing protocol specification almost a decade ago to address this other runout problem. The specific change for ASNs was to allow BGP implementations to support an ASN field that had doubled in size from 16 bits or 2 octets to 32 bits or 4 octets. Unlike IPv4 and IPv6, some effort was made to support a limited form of backwards compatibility in BGP, allowing older BGP implementations to interoperate with new BGP implementations in ways that were largely compatible. The approach was to perform a simple form of ASN translation. The 2-octet ASN BGP speaker would see all 4-octet ASNs such as instances of the same 2-octet ASN, namely AS23456. In addition, the original 4-octet AS path would be tunneled across 2-octet ASN domains by adding an opaque transitive path attribute to BGP. This way, the 4-octet supporting versions of BGP could be deployed incrementally without any overall orchestration. This transition in the ASN number space was managed very effectively. The relatively small pool of BGP speakers, certainly small as compared to the pool of BGP users, and the vendor community was able to field new versions of BGP. And we were able to start incrementally using 4-octet ASNs by 2007, well before we completely ran out of the original 2-octet ASN pool. So disaster was averted in plenty of time, and internet was saved once more, and we headed to the bar, right? Well, not really. The issue is that transition appears to have stalled, as it appears that a significant number of networks want to continue to use 2-octet ASNs. Figure 1 shows the number of allocated ASNs on each day since January 1997. 4-octet ASNs were introduced to the registry system in 2007, yet the rate of allocation of 2-octet ASNs continued unabated until late 2013. A year later, some of the RIRs, I gotta look that up. It's not that. Let's see here. So notably Aaron, RIPE NCC, and IPNIC implemented ASN transfer policies. I think it's like routing information something. So regional internet registries. Yeah, so these are the companies whose job it is to allocate and manage address space, and there's multiple ones depending on the region of Earth. So Aaron, you'll hear about that one all the time because that's for the United States, assuming you're watching this in the United States. But if you're watching it in South America, you'll hear all the time LACNIC. In our case, we're reading from a website that is a blog off of IPNIC. So I think it's reasonable to assume that the author is probably from this region of the world. So let's continue reading. Implemented ASN transfer policies. The outcome of these policies is evident in this figure, where the number of unadvertised ASNs has declined from a peak of 7,300 in mid-2013 to a current count of 3,300. Some 4,002 octet ASNs are now back in the BGP system as unannounced ASNs. So let's take a look at this graph. So here's the date. So 2007 is the date that, let's see here. I thought I saw the word 2007, or the number 2007 up here somewhere. Let's see here. Or 1997. Yeah, 1997 is what I was looking for. Yeah, that's down there. So let's search for, here we go. 1997. Okay, well, that's the first mention of 1997. So that's the RFC number, I know that. But what happened in 2007? So in 2007, 4-octet ASNs were introduced. So that's here. Wait. But why? So time series of 2-octet ASN number use. Okay, so I understand this graph now. So these are all the number of 2-octet ASNs, and if my browser would cooperate with me, please. Thank you. We can see that if we've got 2-octet ASNs, so that's 16 bits. Let's pull up the calculator here. So that's going to be 2 to the 16. So we've got this many available. That's a lot available. I'm surprised they're complaining about there being 600 allocated when you've got 65,000 available. I don't understand. Yeah, I don't understand this graph because, so this is ASN count. So this is how many are allocated in blue here. So there's going to be more allocated than advertised because they're not necessarily using all of theirs. It looks like this is unadvertised, so it should be that the advertised ASNs equal, and the unadvertised, these two numbers equal this number up here. So let's maybe check that. So it's like it's about right here, like 200. This looks like it's about 1,800. So yeah, that looks about right. So as this goes down, the number of unadvertised ones, the number of advertised will go up, but you can see there's, well, not quite as steep of a incline here. Yeah, I don't really understand that graph, unfortunately. If 4-octet ASNs were truly equivalent in every way to 2-octet ASNs, then they would have no particular value over and above 4-octet ASNs, and we probably would not see the pool of unadvertised 2-octet ASNs declining in recent months. However, this appears to not be the case, and 2-octet ASNs are clearly preferred by some networks. Why could this be? The answer could be well contained in the state of BGP communities. Perfect. So now we're talking about BGP communities. So I'll continue to read this. I was actually kind of worried that it truly was clickbait. BGP communities are an instance of BGP update message path attribute. Of a BGP update message path attribute. Yep. So they're going to be optional transitive attributes. A set of values in a BGP community's attribute of a BGP update message is associated with all of the network prefixes or routes listed in the update. It is commonly used by network operators to express the desired handling for routes that could not otherwise be expressed in BGP. In particular, it is intended to be used as an additional signal that may control how these routes are to be accepted by other BGP speakers. And we saw that we changed the local preference to influence the preference of a route, to control the onward distribution of a route, or to describe other attributes of a route that are not directly expressed in the specific path attributes. The original specification for BGP communities, RFC 1997, identified the community's attribute as a variable length attribute consisting of a set of 4 octet values. There were few constraints imposed on what could be used as a value for a community. The specification did define 3 common community attribute values. So these look very familiar. No export, an attribute that intended to prevent the routes from being distributed outside of an AS, or in the case of a network that uses the BGP Confederation construct, out of the BGP Confederation. No advertise, an attribute intended to prevent the route from being advertised to any BGP peer. No export subconfed, an attribute intended to prevent the route from being advertised to any eBGP peer, including eBGP peers in the same BGP Confederation. This set of defined community values has been expanded since the publication of RFC 1997, and there is a maintained IANA registry of well-known 4 octet community values. BGP communities were subsequently extended in RFC 4360 in the form of extended communities. This refinement to the community specification added additional control flags in the form of a type field of 1 or 2 octets and a value field that used the remaining space up to a total size of 8 octets for each community value instance. There were a number of variants in the interpretation of the value field based on the type flags. One variant allowed the specification of a 2-octet ASN in the global administrator subfield, and the remaining 4 octets contained a value that was specific to the ASN. This variant appears to be widely used by network operators to implement a rich policy language to BGP. For example, if you want to advertise a route towards AS291 for NTT America and alter this route's local preference setting, then you achieve this by selecting a community value identified from that company. It's kind of cool. An aggregate collection of published BGP extended community values that influence the handling of a route object by a number of networks can be found at onestep.net. It appears that common use of the BGP extended communities attribute uses the first 2 octets to denote the target network where the policy is to be invoked, and the remaining 4 octets express an intended policy. This construct can allow very precise policy controls on the propagation of a route in BGP. For example, the 4-octet second field of the extended community may itself contain a 2-octet peer ASN and a 2-octet action. so that, for example, you may be able to direct the network AS 64496 to prepend its ASN 3 times to the AS path of all routes propagated towards the peer AS 64500 by using the BGP extended community value 64496:64500:3. Another use is in defense against various DDoS attacks, including a technique called remotely triggered black holes, where the network under attack may opt to push a traffic drop filter onto its peers and further out in the network to allow the attack traffic to be dropped closer to its origination points. The target route is filtered early, allowing otherwise legitimate traffic directed to other routes in the victim's network to have a high likelihood of successful transmission. The reason why BGP extended communities have proved so useful is that BGP operates in reverse. In other words, a BGP route propagates across the interdomain routing space in one direction, while the traffic directed towards the destinations encompassed by this BGP route flows in the opposite direction. Okay, that's hard to wrap my mind around. Hopefully that'll kind of sit and bake in my brain as bread would in an oven. And then when we're in the lab, we can kind of hopefully hear that timer ding and take the bread out, and hopefully it'll kind of freshen up the meal of our lab and make sense in that context. Without BGP communities, it is challenging to orchestrate incoming traffic across multiple potential paths such that the traffic load is even spread across all paths. Network operators use selective advertising of more specific routes and AS prepending in an effort to bias the remote network's path selection process. But such an effort can be challenging and the outcomes are often fragile. In response, many of the larger ISP transit providers have added BGP extended communities to their service offerings, allowing their ISP customers to trigger particular responses. For example, a multi-homed customer could use 2 upstream transit ISPs and use one to prefer to receive traffic originating in Europe and the other prefer traffic originating in Asia. While BGP extended communities have wide acceptance in the network operations area, they are effectively limited to express policy referring to 2-octet ASNs. If one were to use a 4-octet ASN in the global administrator subfield of an BGP extended community value, this would leave only 2 octets for the policy action, which appears to be inadequate for many of today's uses. The result was that in those parts of the internet where 2-octet ASN use in BGP extended communities was well established, notably North America, there was little demand for 4-octet ASNs. As the pool of remaining 2-octet ASNs dwindled, there was a demand to open the pool of 2-octet ASNs to trading and transfers. But this was inevitably only a stopgap measure. What was needed is a standard and widely implemented method of specifying BGP community values with the same expressive capability as extended communities, but able to use 4-octet ASNs. There have been a number of efforts to address this need. 4-octet ASNs, specific extended communities, RFC 5668, proposed a minor change to the extended community specification by lengthening the global administrator subfield from 2 to 4 octets. However, this implied that the local administrator defined value field was reduced from 4 to 2 octets. Flexible BGP communities tried a different approach, using 4-octet originating ASN field and a variable length value allowing up to 255 octets of an associated value. This was not widely supported at the time, around 2004, and did not progress any further. Wide communities took a similar stance with a type length value approach to each community value. The 2-octet length field permitted a maximum value of 65,535 octets. Wide communities certainly appear to have taken a kitchen sink approach to BGP communities, attempting to offer what is essentially a universal mechanism for expressing BGP communities. But sometimes when the hammer you are using is too small for the job, it's not a variably regulated, customizable, percussive tool that you are after. It's just a bigger hammer. Such a bigger hammer is the subject of an internet draft that proposes BGP large communities. This proposal takes the 6-octet payload of the BGP Extended Communities specification, RFC 4360, and simply doubles the size of the individual field values so that the large community values are each 12 octets in length. This proposal also applies a simplification to remove the type field, a feature that appears to be largely unused by the operator community. A variable length approach to wide communities has been avoided. What is left could be seen as a community structure that is close to the original approach of RFC 1997, but of sufficient length to be useful for 4-octet ASNs in the same style of extended communities. This means that the format of the large community value has a 4-octet global administrative field capable of carrying a 4-octet ASN and an 8-octet local data field whose interpretation is defined by the global administrator in Figure 2. This is an optional transitive path attribute. All right, so I think, oh, it's almost done. I'll just read the whole thing. The result is a means of associating community values to routes in the presence of a 4-octet ASNs with exactly the same expressive capability as that provided by extended communities for 2-octet ASNs. The draft specification progressed to the point of a provisional IANA code allocation of attribute code 30 for these large community attributes, and then it emerged that the vendor Highway has been squatting on the same BGP attribute code value in its delayed equipment. Such blatant disregard for the IETF standards progress by any vendor is to be deplored, and Highway is no exception here. But at the same time, expediency demands working around such clashes and drawing a different number from the BGP attribute number space. The BGP attribute code for large communities is now 32. Hopefully we are close to an acceptable simple solution to this issue of using 4-octet ASNs in BGP communities. And if we are so close to an outcome that addresses this issue of 4-octet ASN BGP communities, then perhaps we can now stop looking at 4-octet ASNs as second-class values and use them in precisely the same way we've become accustomed to using 2-octet ASNs. It's about time we completed this work. There are 3,172 available 2-octet ASNs left in the various RIR administrator pools. ARID has none. The RIPE NCC, let's take a look at where that is. So kind of Russia and Europe has the most, it has 2,283. APNIC, I believe that was South America. APNIC, there is no AP. Oh yeah, there is. So, okay, it's not South America, it's Asia and Australia. They have 471, second largest, but Okay, and then the LACNIC, let's see what that is. LACNIC, South America, has 339, and AFRINIC has 79. I like the name of this one because we know that's Africa. AFR, yep, so that's Africa. I really like how that one's named. These LAC, what does that mean with South America? Where is South America in this? And this one here, especially Europe. Is Europe ripe? I don't understand. But, and this one too, AP, I guess A for Asia, that would help. Aaron's easy because I'm from North America, but I think this one has the best name. I like the name on that one the best. At this time, particularly in North America, we are down to the bottom of the barrel. We have already mined 1/2 of the old unadvertised 2-octet ASNs and recycled them back into BGP. This work on usable 4-octet ASN communities is already very late, and we need to complete the work on vendor support, DevOps tools, and operational deployment as soon as we possibly can. For further information on this proposal, useful collection of materials and status of information. So I guess there's more to the story than I would have ever thought. This was only 4 years ago too, so this is pretty cutting edge new stuff, this BGP large communities. So this is kind of its whole thing that is actively being implemented, kind of a good thing to know about if you want to work in advanced engineering, because it seems like it's an ongoing effort. All right, so let's continue. It looks like something failed here. Let's fix that. So, okay, so this is really nice. It gives us the term. Display set, pipe match, route -3. So here's the term. So we're calling large 1-AS. Let's see large 1-AS. This one here, it looks like it hasn't been defined. Let's see what has been defined. So we'll match on this. So I added so I forgot the 1 here when I defined that. So let's fix that. It should be a pretty easy fix. Those are the kind of errors I like. At least in the lab, those are the kind of errors I like because they're easy to fix. Production, it might cause issues. Production, I'm not a big fan of those errors. That's why you would have kind of a different method of configuring the gear in production. Prevent user error. So I think I kind of failed at my goal here, because if we look at those show commands again, so match route, we can see we're calling large 1-AS. Then if we look at the naming I used, I changed the actual community string, but I did not change the name of the policy as it's going to be called. So kind of failed in my attempts to change it, but hopefully that's another really easy one to fix. Okay, so now hopefully we'll be back on our feet. Perfect. Submit it. Perfect, so we're good to go. Let's see if there's any extra information in the step-by-step. Configure the policy that adds large community values to the routes received from device R1. A large community value uses a notation of large. Global administrator, assigned number. These specific community values can be anything that accomplishes your administrative goals within certain parameters. All right, and that's just making sure you got all the configuration on there. So let's move on to the verification and Wireshark as well. And for R1 and R2, we can use our management server. All right, perfect. We've got our static routes here. We've got our communities. It's interesting that they actually don't have their communities on here. Maybe I'm looking at the wrong. Oh yeah, I'm not getting 0.0.0. Wonder what happened to that one. Let's see where. Oh, that's the aggregates. Where is that one? 0.0.0. Yeah, that looks like an aggregate route, so I don't know why they have that and I don't. But I kind of want to just keep moving on. We're going to need to do the, so meaning the output shows that the regular community and large community values are attached to the routes. This is all we're meant to verify in this one. And yep, these have the regular and these have the large. So we've got 2 with the large. I would like to paginate the outputs. We've got 2 with the large, and then we've got 2 with the regular. The communities are attached to static routes, thus demonstrating that communities can be attached to non-BGP routes. Oh, temporary failure in name resolution. So that's interesting. I've never seen that before. Oh, right. So no, I understand what's going on. I'm trying to look at router 3, but I don't have router 3 set up to resolve the name. So let's go in through console because, as I mentioned before, it's kind of too time consuming to set it up through the server. So show protocol BGP match prefix 16 dots detail. Oops, looks like we've got some problems on R3. The output shows that the regular community values remain attached to the routes and the large community values are added. So, so we'll see multiple here, but I don't understand how they expect this to happen if there's no eBGP connection set up between device R1. Oh, there is an eBGP, okay. And device R3. Oh, there is. So let's see if there's an issue with that configuration. Okay, everything looks good there. Let's verify that the BGP neighborship is up. Aha, so it's in idle. So let's see if the connection between the two is up. Aha, we can see we've only got an IP on that port, so we're missing the IP configuration. Let's see if it's missing from this side as well. So we've got it on this side, but so this is the R3, but we're going to need it on the other side on R1. It's going to be a port G1. So let's put that on there. It's going to be 13. Okay, so R1. Oh, okay, that's interesting. This is R1. It says to put 14 on R1. But then on R3 it says to, oh, it does have to be 14, okay. Come on, let me do the thing. There we go. Oh, wait, no, that's not it. Oh, I did one. Okay, so now hopefully the BGP connection will come up. Sent. Hopefully there'll be time to get a Wireshark capture going on that. Usually it takes a while, especially when you have that race condition. Looks like I didn't get there in time, so I'm just going to roll back one commit, and then I will reapply that change once Wireshark is up. Seems to be having difficulty right now. Ooh. Yeah, so for some reason, here we go. We've got this classic error that happens sometimes, so that's okay. Well, I kind of don't want to forego Wireshark, so I think I'm going to give it the good old-fashioned restart. It's really not a problem to do. Just restart it. Looks like our server is there too. With the restart, everything kind of goes better. There we go. Now we can stop the capture. Start it again. We can see the connection collision as well. We'll see that. So, but I need to go on router 3 and I need to roll back that configuration in order to see it. Well, actually, it's going to be on router 1. Perfect. So now, hopefully, we'll see that collision, connection collision resolution. Oh, it's established. Oh, I see. So what happened is it never hit that hold time. So it takes 90 seconds for it to actually go out from established. So it never hit that time where it actually tore down the peering. So even though the peering wasn't technically up, BGP never realized that it wasn't technically up. So it never sent out that extra update to tear it down. I'm surprised we're not seeing keep alives though. We should be seeing keep alives. I think there's something wrong with the capture, probably because Wireshark is trying to update itself. It's going wonky. I mean, I'll just do the update. Well, we should see this drop eventually because it's no longer got that correct IP on there. Aha, so this is what I was more expecting to see, some update messages, but we're only going to see, or sorry, some keep alive messages, but we're only going to see those from 13. We won't see them from 14 because 14 is now down. And in fact, we're going to see a bunch of extra ARPs too now because it's no longer even in the ARP table. So it's going to ARP and try to, like it's confused why it can't get there. So it's going to send out extra ARPs. Okay, now we are inactive. So we'll see that connection collision. We'll see those ARPs go away. And we'll see a three-way handshake and some update messages. And those update messages will have and there's the gratuitous ARP because that now has the IP and is ARPing. So I'm kind of surprised that the IP address of the gratuitous ARP is the same here. And it looks like the Wireshark capture stopped again, unfortunately. It seems to do that whenever I bring up an interface or something like that, or do something like really dramatic on the device. It seems to tank the Wireshark capture, which I guess makes a lot of sense. Like if the link goes down, you know, how can you sniff the link? So maybe it's every time the link goes down, the capture stops. But let's try it again, and hopefully that's not the case, and hopefully we can just get lucky and get it this time. Oh, it looks like it's not stopping too, so another bug. Here we go. Yeah, because I want to see that connection collision one more time. I want to see the routes actually being passed in the update with the additional optional transitive routing communities. So remember, we're going to have to wait for it to go into active though before we hit it, or else it won't reestablish. Well, let's see what happens. So I'm going to bring that up. We're going to see a gratuitous ARP for that being up. There it is. Aha, so now, oh, it looks like we do reestablish the three-way handshake. I thought that wouldn't happen because it hadn't. Oh, but we can see it actually, let's see here. So, Well, no, it never went into active. So it looks like even though the hold timer didn't expire and it never actually severed the connection, it just kept the keep alive, it was able to reestablish the connection. So let's take a look at that update message. Oh, we got a bunch of them. And hopefully we'll see the communities. Yep. So we've got an update message for each of the routes that we're sending. So, and here's the large community. Yep. See how much extra that takes up versus the regular community. All right. So I think that's everything. Let's look at the documentation again. So yeah, that's everything. So let's cross it off. And okay, so we finished the whole topic on BGP route communities. I feel like I have really good confidence in that. I can really, I think, troubleshoot anything going wrong with policies. I just got to look at the import policy and make sure that it's matching a BGP community. I've got to look at what the BGP community is. So I feel really confident with that. So let's mark this off, and then we've got one last topic in the BGP implementation section. So, and then when I'm done with this final one and we mark off this whole section, we can do some math to see how I'm doing time-wise, and if that September 9th or September timeframe for taking the exam is reasonable or not. And if it turns out to not be reasonable, I'm going to need a lot more time. I can kind of tighten up these videos, tighten up my sessions, and what I would have read an entire blog post on BGP large communities. I'll just say, well, does the curriculum say large communities or the curriculum just say communities, and kind of scale back the amount of research and study I put in. So stay tuned for the next video on IPv6 tunneling. Thanks for watching.